Hello students, variation of resistivity with temperature, or you can say variation of resistance with temperature. Now we want to create a mathematical relation for that, and based on that relation there will be a numerical in board examination. This topic is very important because this is kind of hidden topic and teachers try to frame the question from here. So let's begin. Okay, this is already known that resistance is directly proportional to length upon area. So we are picking up length first. If we increase the length, what will happen to the resistance? It will increase. Okay, now if we increase the temperature, the metal and alloys, they expand. When they expand, you can say length will increase. When length increases, R will increase, resistance will increase, and now this will give us an idea that we can relate temperature and the length. Now it is a case of expansion. So in case of expansion, you know already there is a change in length. So change in length of a material is directly proportional to its original length. Then there is a change in temperature. So if you remove this proportionality constant, you will get an alpha, which is the constant for expansion, linear expansion. Now you know there is a change in temperature can create a change in length. Because of this change, the resistance will change. If you increase the temperature for metal and alloys, definitely their length will increase. Because of that, resistance will increase. The name of the alpha is temperature coefficient of linear expansion. Okay, so now this I will use to create a mathematical relation between change in temperature and change in resistance. How I will do that? So you just see one thing, that if resistance is directly proportional to length, so what I will write, change in resistance will be equal to proportionality constant multiply by original resistance multiply by change in temperature. I can write this equation because resistance is directly proportional to the length of the conductor, and if there is a change in length, then there will be change in resistance. So change in resistance is also directly proportional to change in length. That is why I can reach to that relation. Now this relation is very important for us. Like if you want to write a formula for a resistance at a particular temperature, so how can you write this? So resistance at a temperature T. So let's say temperature T. So how can I write this? So this is the final value. The final value contains R0, original resistance, plus whatever the change in resistance due to the change in temperature. Now put the value of delta R. So it will be alpha R0 delta T. So this is our equation. We have now RT, resistance at a particular temperature, will be equal to R0 original resistance and alpha temperature coefficient of resistance, and there will be an original resistance, and the finally is change in temperature. This may be a rise in temperature or maybe decrease in temperature. Both can be possible. Now from here, I want to find out the value of alpha. Let me tell you one thing. This is the relation based on we'll have numerical in board examination. For this, I will prepare one separate video especially for the numerical based on this part. Now, I want to find out the value of alpha from this equation. So how can I get this? So just rearranging the terms, let's take R0 to the left side and then write down this. This is the first step. Then second time, I just take alpha on one side and put all the other terms to the another side like this. Is that okay? Now this alpha is actually here, that is temperature coefficient of resistance. temperature coefficient of resistance. Now this alpha, we need to define this alpha as well. So let's define it, and it's very easy. If you know this formula, you can easily define that alpha. How can you do that? Let's see. What is this part? What is this numerator is? Numerator is saying difference in resistance. That means change in resistance. Okay, so I'll write change in resistance first. Change in resistance. Okay, and the second thing is we have another part in denominator as well. What is this? This is original resistance. Original resistance. Yes, this is original resistance. And then finally multiply by change in temperature. What is it then? Change in temperature. This you need to remember. You need to write down change. Don't write increase and decrease. Many a time students used to write rise in temperature, but rise in temperature is not the only correct thing. There can be a decrease in resistance. That is why you should write change in temperature. Okay, now let's define it. What is temperature coefficient of resistance? You can define it like this. This is equal to change in resistance. This is equal to change in resistance per unit original resistance per unit change in temperature. Simple thing. I'm just repeating it. Change in resistance per unit original resistance per unit change in temperature. Next thing is its SI unit. What is the SI unit of this alpha? Temperature coefficient of resistance. You can see from the formula, numerator has change in resistance. That will have a unit of ohm. Then you have a numerator and in which you have a ohm again, because there is a original resistance. And there will be a change in temperature, and temperature will have a unit of Kelvin. So ohm and ohm will cancel each other. You will get finally Kelvin inverse. This is the SI unit of alpha, temperature coefficient of resistance. This is the unit of alpha. What is alpha? Alpha is temperature coefficient of resistance. Now let's do few more things with this alpha. Let's write down the formula of alpha. So alpha is RT minus R naught divided by R naught into delta T. So this is alpha. Now from here I want to find out the value of alpha. We are not going to find out the value actually. We will just estimate it, whether it is large, small, or maybe negative. Can it be negative? So let's find out. So now we have alpha, and so we have three types of materials. One is metal, alloys, and then we have semiconductors. Okay, so for metals we have done a graph. From that graph we'll take a reference of that. If we increase the temperature, resistance of metal will increase in large amount. So as you see, this RT and R naught value will be large for metal. So can I write change in resistance, and that is RT minus R naught is large. Large for what? For metals. So it is large. When this term is larger, so obviously alpha will be larger. So alpha will be large and positive also. So large, positive. You can write down alpha for metal is large, positive. Is that okay? Because the resistance increases much greater than alloys. Okay, now let's go for alloys. In case of alloys, you have seen there is a flatter curve, more flatter curve between resistance or resistivity and temperature. Now you see here, if it is more flatter, so yes, RT minus R naught, which is change in resistance, is positive. That is okay. The second thing is it is small. So the value of alpha for alloys, it will be small positive, small positive. Okay, now can you guess what will happen to semiconductor? So you know already. So we have a graph for semiconductor as well with temperature, and their resistance will decrease. On increasing the temperature, resistance of semiconductor decreases. Because of that, this RT minus R naught, can you tell me what will be the value, positive or negative? So it will be negative. So this change in resistance is negative here. So as delta R is negative, so alpha will be negative. I'm going once again. So alpha for metal is large positive. Alpha for alloys is positive but small, and alpha for semiconductor is negative, because on increasing the temperature, resistance of the semiconductor decreases. That is why it is negative. So this is what you need to understand about this temperature coefficient of resistance. Now let me tell you one more thing which is quite obvious, that if we have a relation for resistance which is RT equal to R naught plus alpha R naught delta T. Similar kind of equation I can write for resistivity as well. So resistivity at any temperature will be equal to original resistivity plus alpha. That is, now you need to pronounce this alpha as temperature coefficient of resistivity. Is that okay? So when you are talking about resistance, you have to do it for resistance. When you are talking about resistivity, you have to say temperature coefficient of resistivity. And if for resistance, you will say temperature coefficient of resistance. Here alpha is temperature coefficient of resistivity. So I can write again rho naught and then rise and then change in temperature. And then change in temperature. So this is, let me just write temperature coefficient of resistivity. Is that okay? Now whatever we have done with the resistance equation, so now we are doing the same thing for resistivity equation. Then alpha equal to rho T minus rho naught divided by rho naught into change in temperature. The same equation. For your reference, I just want to write down the equation for resistance as well. So RT minus R naught divided by original resistance into change in temperature. These are the two same things. Now you can define alpha similar to the alpha when we are talking about resistance. Let's do it once. So temperature coefficient of resistivity will be equal to change in resistivity per unit original resistivity and per unit change in temperature. So you can do in that same way, and unit SI unit will be same. That is per Kelvin. Is that okay? Now remember, degree Celsius is not the SI unit. I can write degree Celsius per degree Celsius also, but that is not a SI unit or not CGS unit. Hope you understand the topic. Thanks for watching.